Over the years, researchers have tried to limit the value of the Hubble constant. Still, the results added more to the confusion every time, rather than clearing things up, leading to a cosmology crisis. But before moving to this crisis, let's try to understand what the Hubble constant portrays in the physical sense. The Hubble constant is a significant number in cosmology. It can help have an end-to-end test of our understanding of the universe, from the Big Bang to its final fate. The physical representation of H0 seems easy to comprehend, but if it is so easy, why is it so difficult to obtain a precise value of the Hubble constant? Why is it considered a notoriously tricky entity to calculate? The answer lies in the parameters involved to evaluate the same. To calculate the value of the Hubble constant observationally, we need two quantities: the recessional velocity of a galaxy and its distance from us. The recessional velocity can be measured by observing the wavelength shifts of spectral lines emitted by the object, known as the object's cosmological redshift. However, the second parameter, the distance, is comparatively problematic. One of the standard ways to measure the distance to a galaxy is via observing the Cepheid variables residing in it. Like all other variable stars, Cepheids progress through a complete cycle from maximum brightness to a minimum and then back to maximum again. A Cepheid's variability period is directly related to its luminosity. The longer the variability period, the more luminous the Cepheid is. Astronomers observe the Cepheids and compare their apparent brightness with their intrinsic brightness. Then, by measuring the difference between the observed and actual brightness, one can estimate their distance using the distance modulus equation. In this way, Cepheid variables act like standard candles, and Edwin Hubble used these variable stars to measure the distance in the first place. However, before making calculations, the period luminosity relationship has to be calibrated with nearby Cepheid variables, whose distance can be measured using the parallax method. This stepwise measurement of cosmic distances is called the cosmic distance ladder, and the problem is that the uncertainty compounds with each step. Edwin Hubble was able to plot the variation between the distance and recessional velocity for 46 galaxies, thereby obtaining a value for the Hubble constant at 500 kilometers per second per megaparsec, or about 7 times what astronomers think it is today. Cepheids can only be used to measure distances from about 1 kiloparsec to 50 megaparsec. So what about the distances greater than this range? We cannot fix a constant's value just by observing the behavior of galaxies up to 50 megaparsecs. We need to peer further for precise estimates, and that's where the Type 1a supernovae come into the picture. A Type 1a supernova occurs when a white dwarf, feeding upon its companion, undergoes a runaway fusion, eventually exploding into a supernova. Such supernovae explosions are exceptionally bright, making them excellent standard candles to calculate longer distances. The Hubble SHOES program, which stands for supernova H0, for the equation of state of dark energy, has made significant contributions to calculating the universe's expansion rate using these supernovae. In 2019, the SHOES team reported a value of Hubble constant around 74 kilometers per second per megaparsec. The SHOES project considers the galaxies lying within 2 billion light-years away, which means that it measures the present expansion rate of the universe. To make sure that this value is correct, one must be able to verify it with theoretical predictions. And to make those, we need to travel back in time. That's because if we can measure the universe's expansion rate just after the Big Bang, we can use that value to make estimates of the Hubble constant for the present-day scenario. And when researchers did this, a crisis broke in front of them. After the Big Bang, we know that the superheating of all the matter in the universe released enormous amounts of energy. As the universe expanded, the radiations got more and more redshifted. The cosmic microwave background, or CMB, proves to be extremely helpful in estimating how much the radiation redshifted. The CMB is the remnant electromagnetic radiation from the early stage of the universe, and it is not uniform. Instead, it's made up of hotter and colder patches that signify the clumpiness of matter and energy in the very early universe. Researchers combined fundamental physics with estimates of the amount of mass and energy contained within the universe to model the expansion of the universe from its initial state to the present day. Consequently, with the precision obtained in different methods, the best measurement appeared to converge on a value between 67 to 68 kilometers per second per megaparsec. That's clearly different from what the observational values say. The mathematical predictions expect the universe to expand slower than that calculated from Hubble's data. And this has been one of the biggest crises in cosmology so far. Researchers have been trying to achieve greater accuracy in their observational values, and recently, they've reached a new milestone in this domain. The SHOES team reviewed all the data taking into account over 1,000 Hubble orbits and analyzed 42 supernovae milepost markers that are exploding at a rate of about 1 per year. This almost marks a complete analysis of all the supernovae accessible to the Hubble Space Telescope so far. Finally, they converged on a Hubble constant estimate of 73 plus or minus 1 kilometer per second per megaparsec. This value is again higher than the theoretical predictions of 67.5 plus or minus 0.5 kilometers per second per megaparsec. But the measurement is about 8 times more precise than Hubble's expected capability. And given the large Hubble sample size this time, this is only a 1 in a million chance of the new estimate being wrong. Although the cause of the discrepancy between the predicted and observed values of the Hubble constant remains uncertain, the new results are expected to open the door to discovering new physics. Astronomers are also looking for new phenomena and objects to measure the distance of the universe. They include neutron star mergers and red giant stars. Also, with NASA's Webb Space Telescope coming into full swing soon, we can expect to have sharper resolutions and even more precise results in the future. And this has been one of the biggest crises in cosmology so far.